I'm Robert. I'm full professor for design automation at the Technical University of Munich.
Hi, I'm Kevin Mato, and I'm a PhD student in this group.
And in this video abstract, we want to briefly introduce you to design automation methods and software for mixed-dimensional quantum computing. Of course, you already know about quantum computing in general, right? Qubits, superposition, entanglements, and so on. And you probably know that those systems often assume two-level basis states. That means qubits with zeros and ones. But the technology also offers for multi-level qubit systems. That means systems based on qudits rather than qubits. And they offer much more potential. In the project Next Level Quantum Information Processing for Science and Technology, which is funded by the European Union under Horizon Europe, a great team of researchers from various fields is currently exploring that potential. And our task in this endeavor is we want to develop corresponding design automation methods and software tools that allows end users to easily simulate and compile corresponding systems. And already in the first part of that project, we were able to come up with some initial but really helpful tools. And Kevin here is now going to briefly summarize those tools, some of those tools, and then afterwards also will provide a brief tour, some hands-on experiences, how to use these tools.
Great, let's go. Let's take a look at our Envision Flow. Mixed-dimensional quantum architectures have been proved to be naturally suited for solving a variety of problems, such as high-dimensional quantum simulation, integer optimization, quantum data compression, or quantum machine learning. For this reason, we have introduced a new way to specify these problems in terms of quantum circuits, via an extended open QASM for qudits or a Python interface. These quantum circuits then can be efficiently manipulated and represented by data structures and methods such as graphs, machine learning, heuristics, tensor networks, or decision diagrams. And these last ones have been used for developing a mixed-dimensional decision diagram simulator, for example. We have also added the possibility of creating noise model specifications and also fake backends in order to simulate your quantum circuits with realistic error rates. Here you can see the reference to one of our contributions. In our flow, we have also a compiler made of passes that could potentially guide a user in the compilation of qubit circuits into a qudit machine, or in the task of state preparation, entangling operations compilation, single qudit operations compilation. Here also some references to some of our contributions. Lastly, the sequences produced by a compiler can be executed on a qudit machine and then compared to the results of a simulation. Okay, let's take a look now at this Jupyter notebook and let's try to understand how the Envision Flow is put into practice. Okay, we can first of all import our quantum circuit and a quantum program in terms of a DIT QASM. We can now construct a quantum circuit directly from the QASM, and we can see that we have 4 operations and 5 qudits. In this case, it's 2 qubits and 3 qquints, or 5-level qudits. But we can also construct a quantum circuit from scratch, and we can first of all create a quantum circuit, create 2 quantum registers. Each one of them is made of only 1 qubit, and then we can apply operations to these qubits, 1 Hadamard, and then a CSUM. The most interesting fact here is that we can apply operations to qubits, but we don't have to take care of the representation of these operations, because the code will automatically detect the size, dimension of each qubit and apply the right operation to each one of them. Then we can also export and share our circuit with our QASM specification. In this case, we can print it directly to QASM, but we can also export it to a file. Then we can simulate our circuit. In this case, we have 2 engines, a tensor network simulator and our mixed-dimensional decision diagram simulator. And we can call a backend, in this case a tensor network simulator, and we can perform a simulation. Okay, and the result is that the 2 qubits of our quantum circuit are in a perfect superposition. We can also call a fake backend. In this case, it's an ion trap device made of 2 qubits, and we can compile our Hadamard into a sequence of pulses compatible with the ion trap machine. The result is a sequence of 9 given sortations plus the CSUM for a total of 10 operations with a circuit still of 2 qubits. And we can also perform our simulation with the integration of a noise model. And in this case, we can see that by simulating the compiled circuit on our ion trap machine, the result is that we don't have a perfect superposition anymore, but we have fluctuations due to the error rates of the single operations.
All tools and the shown Jupyter Notebook are made available as open source implementations as part of our Munich Quantum Toolkit.
Links in the video description below will lead you to them. If you like them, if you have any feedback or any comment, please feel free to reach to us.
We would like to thank our great partners from the Next project for the nice collaborations and the European Union for funding us through the Horizon Europe program. Thank you very much and take care.
Thank you. Bye-bye.